Hey everybody, welcome. Thank you for coming to today's Colloquium and Job Talk. It's my pleasure to introduce Anshul Shah. Anshul is a PhD student in computer science at UC San Diego. He was an undergraduate at Duke, where he double majored in statistics and computer science. He has won a very long slew of awards, both for research and for teaching. You can read about that on his website. I've also learned that he's an avid surfer. I've warned him that the waters here may be less than satisfactory as far as surfing goes, but he let me know that he's also been getting into tennis. So I think we have at least 2 faculty in the Allen School who are like ranked tennis players, so there may be some affinity there. Anyway, I'm very excited for this talk, so please take it away, Anshul.
Sure. Thanks for the introduction, Ben. Hello, everyone. My name is Anshul Shah. I'm at UC San Diego, and I'm a computing education researcher. It's an exciting time in computing education research. We're facing some unprecedented challenges, but also some promising opportunities to adjust the way that we teach computing and prepare students for modern software development. So let's go ahead and get started. I want us all to imagine a typical programming course of today's day and age. We'll have anywhere from several dozen to several hundred students, and they'll be working on a programming assignment. Now, when the deadline for that assignment arrives, students will submit a final version of their code. And the course staff, tasked with assigning grades to all of these submissions, will typically use some sort of an autograder to give correctness feedback to students. Now, there are some real advantages to this cycle. It's scalable, and it provides timely and objective feedback to students. As soon as students submit their code, they can know what grade they received, and they can know exactly why they received that grade based on the test cases that they passed. But there's also a real concern to this cycle as well. And the concern is that instructors know only what students have created, but don't know how students created it. Now, in this programming assignment cycle, we have 2 elements at play. The first is the process that students use to create those final code submissions. And then we also have the final code artifact itself. Now, computing education has heavily studied that final code artifact. It's easy to collect. All the students are making a submission. And it does give us insight into students' ability to correctly implement a programming solution. But what has been understudied are students' programming processes. And when I say processes, I mean the skills that they're using to create that final code artifact. Skills like debugging, code comprehension, testing, and more. The central focus of my research is to understand what happens during the programming process. I believe that by comprehensively answering this question, we can unlock all sorts of pedagogical innovations, like process-level feedback to students, personalized coaching, and new grading schemes that not only prioritize a correct final code artifact, but adherence to good programming processes as well. So why is it even important to consider and improve students' programming processes? Well, the motivation for my work is the academia-industry gap in software engineering. So let's walk through some of the differences between programming in universities and programming in industry. Students are primarily coding from scratch, from a blank file or workspace in a process called greenfield development. Software developers work on large existing code bases in a process called brownfield development. Students are submitting a final version of the code that they've written, but in industry, there's this heavy emphasis on an incremental and iterative process. Students are primarily graded on the correctness of their code. But in industry, there's a variety of other factors to consider, like security, efficiency, and maintainability of the code that they write. And lastly, academia has been relatively slower to adopt GenAI due to valid concerns about hindering students' learning. But in industry, we're already seeing a widespread adoption of GenAI. Now, my claim is that this academia-industry gap is imperative to address pedagogically. So let's break down what I mean with this claim. Why is it even imperative to address this academia-industry gap? Well, for students, we offer better career readiness and value for their college degree, which is increasingly important given the broader social discourse about the reduced value of a computer science degree. and companies spend less time and money on the expensive onboarding process. But why should this gap be addressed pedagogically? Why should it happen at institutions and universities? Well, some suggest that internships are a great way to prepare students for industry, and they're mostly right. But as of 2020, only 57% of graduating students from universities completed an internship by the time that they graduated. And more alarmingly, internship participation was associated with socioeconomic status, leading to real concerns about equal access to getting a foot in the door in the software engineering industry. And also, this 57% statistic is from 2020. This number might even be lower now due to GenAI. Yeah, go ahead.
Do you have a sense for what the university sample were?
For the university what, sorry?
In the 57% completion rate?
Yeah.
Is that only R1s? Is it slacks? Does it include community college?
Good question. So this study was from the University of Florida, but I think they surveyed students from around the country. I don't have a sense of what that breakdown was like at different universities. But if it's mostly at University of Florida, then I guess that's like an R1 in Southeast US. Yeah. And the last thing on here is recent work from my lab, actually, at UC San Diego showed that regardless of a faculty's sub-discipline in computer science, they value imparting software engineering skills as an important outcome of their undergraduate's computer science education. As a result, the goal of my research is to address the academia-industry gap by imparting effective programming processes to students. Now, in this programming assignment cycle, I've done work to understand students' processes. For example, I've studied students' incremental development practices, their help seeking, and how they comprehend code in a large code base. I've also studied the final code artifact of students, considering the code quality defects that they introduce when working with a large code base. And I've also done work to understand students' behavioral engagement during lecture, and some theoretical contributions about a theory of teaching and learning called cognitive apprenticeship that is used in some computing education courses. But for today's talk, I'm going to focus on incremental development, program comprehension in large code bases, and students' collaboration with AI assistants and agents. This is the roadmap for my talk. You can follow along at the bottom of each slide. Let's get started with incremental development. Incremental development is a fundamental programming process that involves a student writing a little bit of code and testing it as they go to keep the debugging and testing process manageable. Now, recognizing that this is an important process, many instructors choose to demonstrate their programming process to students during a lecture. Now, this is a widely used teaching style called live coding, and it's even a recommended technique, especially at the introductory level in CS1 and CS2 courses. However, when I started my PhD, the existing research on live coding tended to only study instructor and student perceptions of the teaching technique. And both groups, instructors and students, felt that live coding improved students' programming processes, that it should improve students' learning, and that it increases students' behavioral engagement during lectures because there's a dynamic process happening in front of them. But the evidence to support these popular perceptions was limited to non-existent. And so the first line of work I conducted was to understand the actual impact of live coding across these three student factors. So to begin this line of work, I created a metric using students' programming process data, essentially a snapshot of their code every time they pressed run, to create a metric to quantify how well students adhered to this process of code a little, test a little. And after creating this metric, I conducted 3 term-long classroom studies to compare live coding to a popular alternative called static code, where the instructor shows an already written correct piece of code and perhaps annotates that piece of code to support students' comprehension of that. Now, I studied the outcomes across these 3 student factors. For example, in student learning, I considered their grades on assignments as well as final exams. We looked at students' performance on code writing, code tracing, and even code explaining tasks within those exams. And we also used pre- and post-lecture questions to see how much learning happened during the lecture sections themselves. Now, for comparing students' programming processes, I applied my metric of incremental development to see how well students adhered to incremental development during these proctored programming sessions. And I also applied metrics related to debugging, like an error frequency metric, and also considered how frequently students were testing their code and adding diagnostic print statements in their code. I also studied students' engagement, including surveys about how well they felt that the teaching style facilitated note-taking, and also did a study to understand students' behavioral engagement during these different teaching techniques. So to just get a sense of how we quantified factors like programming processes and behavioral engagement, I mentioned that I collected students' programming process data, a snapshot of their code every time they pressed run. And so we were able to apply a metric called the repeated error density, which looks at the exact error message that students get as a result of each of those snapshots to see how frequently students were running into errors and how quickly they were able to debug those errors. And I also applied my measure of incremental development by considering how much code students added, edited, or deleted in between runs. Now, for measuring students' behavioral engagement, I applied a protocol called the Berry protocol. This was created in 2015 to understand behavioral engagement in a large university lecture. And in this protocol, a researcher and maybe some of their research assistants sit at a specific location in the lecture hall. So this is rows and seats in a lecture hall. I'm sitting in row G7. And you pick out 10 students to observe throughout the lecture. And every 8 to 10 minutes, you apply a rubric that's part of that original Berry protocol to quantify how many of those 10 students are engaged at that particular observation moment. The results that I found did not align with the popular perception of live coding. I found no evidence to support the fact that live coding improved students' programming processes, no evidence that live coding improved students' learning, and actually, students felt that live coding was worse for their engagement because they were unable to take notes well during the live coding lecture. So for example, these are comparisons of students' performance on code tracing and code writing tasks on a proctored in-person final exam, showing no difference between the static code and live coding groups. In terms of adherence to incremental development, there was no difference, statistically significant difference, between the two groups in their adherence to incremental development according to my metric. And lastly, in an anonymous survey, more students felt that live coding did not facilitate note-taking. I think the idea is that if a student gets lost about 2 minutes into a live coding lecture, they're sort of checked out for the rest of the lecture because of this dynamic process in front of them, sort of leaving them behind. In a static code format, students are able to easily copy down the code example and annotate as the instructor is annotating. Yeah, go ahead.
You mentioned this Berry protocol before, and
yes.
Here you have self-report. Do you also have, is it conflicting data from the Berry protocol?
It's not conflicting data, and I'll get there in 2 minutes. Okay. Yeah, it's a really cool graph you'll see in a second. Any other questions? OK, cool. So recognizing these surprising results of live coding, I created a variant called active live coding, where the instructor still has this traditional live coding segment, but then the students extend the code example from the instructor and then discuss with their peers, adding an active learning moment. And in this, we did see an improvement in student engagement. So now I'll answer Gilbert's question here, where this is actually an average over the 15 lectures that I and undergraduate research assistants observed, showing how engaged students were throughout the lecture associated with specific activities in the lecture. So for example, where this red circle is, this shows that 30 to 40 minutes into the lecture, only 65% of students were engaged in this traditional live coding lecture. All right? But when we introduce active live coding, we see this huge increase in student engagement during the active live coding moment. And that itself is not a surprising finding. When we tell students that they have to add some code and do something during a lecture, they tend to do it. But what was interesting is we saw a persistent engagement effect even after the active learning moment. For up to 20 minutes, we saw a 25% increase in students' behavioral engagement after the active learning activity. However, despite this increase in behavioral engagement, we saw no evidence that active live coding improved students' programming processes or their learning as measured by performance on the midterm and final exam. So what was the impact of this work? In computing education, we separate the impact in terms of advances of knowledge, sort of the research contribution, and then the actual implications for educators. So the research contribution is that I conducted a rigorous evaluation of two of the most common teaching techniques. I also created this measure of incremental development, and a group of researchers at Utah State actually further studied this metric and showed that there was no correlation between students' incremental development behaviors and their score on the programming assignment, actually highlighting my concern that I raised at the start of the talk, that our assessment of final code artifacts do not depend on the process that students use to create those final code artifacts. And in terms of implications for educators, a big finding is that live coding may not be worth it. As I go to these different conferences in computing education, a surprising number of instructors tell me about the impact that my work had on the way that they actually teach programming, especially at the introductory level. However, we did find that active live coding, which actually takes a bit of a burden off of the instructor to have 10 minutes of the students coding and discussing with each other, did increase engagement by about 25%. And this paper, although it was a journal paper, was selected to be presented at our practitioner-facing conference called SIGC last month. And my work to show that live coding did not facilitate note-taking actually led to a group of researchers at Virginia Tech creating a tool to facilitate note-taking during a live coding lecture, where the students can actually see the instructor's live coding example, they can annotate the code, and even take notes easily on the side of the coding example. All right, now let's take a step back for a second and consider a developer's career progression. Oh yeah, go ahead.
So just to understand, when you say live coding,
Yeah.
is it just the instructor who's coding, or is everyone coding along on their laptop with the instructor?
So it means that it's instructor-led live coding, where the instructor is programming. But to the second part of your question, does it mean that students are following along? Not clear. Some students may choose to follow along, some students may not. And that's actually one of the perceptions of live coding before my line of work, is that live coding can turn into a passive activity where students are just watching, and if they get lost in the example, they may not actually be engaged in the dynamic process happening in front of them.
I guess what I'm wondering is, what if the whole thing is active, basically, right? So it's like everyone has a laptop, and they're kind of doing the same thing the instructor is doing.
Yeah, I think that's the goal, where we tell students you can follow along and type along as I'm doing the live coding lecture, but in practice that may or may not be the case. And as my observational study showed, only about 60% of students are behaviorally engaged during a traditional live coding lecture. So even if we recommend that, in practice that's not what's happening. Yeah, any other questions? Cool. Okay, so now let's revisit this developer's career progression. Okay, we have two ends of the spectrum. We have when they started programming as first-year programmers on the far left, and then we have software developers on the far right of the spectrum, and then early career developers somewhere closer to the middle. All right. Computing education tends to heavily focus on first-year programmers. In fact, my live coding work that I just discussed is situated at the far left of this spectrum. And then software engineering research, especially empirical software engineering research, tends to heavily study software developers and early career developers. What is understudied by both research disciplines are upper division undergraduate students who are actually making that transition from novice programmers to early career developers. And after recognizing this, the rest of my research actually focused on this understudied population. So with that, let's talk about program comprehension in large code bases. As I mentioned earlier, students in university courses are primarily engaging in greenfield development, where they'll start from a blank file or workspace and add code to it. In contrast, developers take an existing large code base, have to understand part of it, and make a relatively small modification. Now, in this process, why is program comprehension even important to consider? Well, a study from 2017 looked at how much time developers spend on different tasks when making a modification to a large code base. And the results showed that 58% of a developer's time is spent understanding the code. An additional 24% of the time is just spent navigating between the different files and classes in the code base. And just 5% of the developer's time is spent editing the source code itself. Now, whenever I present this slide, I get this classic question, does this change in the age of generative AI? And the answer is yes, definitely it changes. But program comprehension itself is still an extremely vital process for effective collaboration with AI assistants. I'll talk about this more in the future work, but one, the amount of time spent and needed for code reviews has significantly increased, and understanding is a prerequisite to this code review process. And similarly, Margaret Ann Story, a software engineering researcher at the University of Victoria in Canada, introduced this concept of cognitive debt, where when developers or even students are working with these AI tools, rather than technical debt being the buildup of design and code quality issues, cognitive debt is a misunderstanding or lack of understanding about the design of the application and what the different pieces of your software are actually doing. Regardless, to address this gap in the academia industry differences in programming, I led the writing and planning of an NSF grant to address this key gap between academia and industry. And in this grant, it laid out 3 phases of my work. The first was to identify student struggles when working with large code bases. And my main contribution here was a paper at the ICER 2025 conference, the premier CS education research venue, to understand student struggles to comprehend a large code base. Now, this paper was awarded the Best Paper Award at this conference, and in it, I used a popular human-computer interaction theory called information foraging theory to model students' code navigation and program comprehension processes in a large code base. Now, I want to talk a little bit about this theory itself so you can understand what this study was all about. So information foraging theory, as I mentioned, it's an HCI theory to explain how humans search for information in an information-dense environment. Think reading many news articles on Google after you do a specific query. Now, information foraging theory comes from a biological theory called optimal foraging theory. And let's go through this quick analogy here. Let's say we have a cheetah that wakes up from a nap in the middle of the savannah. The cheetah smells some apple trees to the west. They smell some meerkats to the north, and some gazelles to the east, okay? Optimal foraging theory tells us that the cheetah will decide which food to pursue based on the value of the food and the cost to pursue that food. So for example, the apples are relatively easy to pursue because they stay in one place, but their perceived value is lower because it's less calories and maybe less tasty than the gazelle. However, the gazelle is extremely hard to pursue because gazelles are so quick and nimble. Now here, we're working with information, not food. So what is the information foraging process? Well, it starts with us picking up an information scent. These are cues or inferences about where relevant information might be located. So when you do a Google search, you'll see the name of the publisher on the Google search result before you actually click on the article. And you might even see some bolded text to indicate what might be overlapping with your specific query. Then we engage in a foraging activity. For example, doing the Google search itself is a foraging activity. And then we might be aided with an enrichment. These are things that increase the value or lower the cost to pursue that information. So it might be like sorting your results for most recent results. And then finally, we consume an information diet, which would be the actual news and words that we read. Now, we can actually operationalize the information foraging process to the context of understanding a large code base. For example, the information scent would be some of the inferences about where code might be located. The foraging activity would be things like reading code itself, scrolling within files, or browsing different file names to find some code, and so on and so forth. Now, in this study, the goal that we had was to understand where in this process students are actually struggling. For example, are students failing to pick up on the right inferences and have good intuition about where to find something in the code base? Or maybe students do have strong intuition, but they're unable to act upon that intuition by using good foraging activities or code comprehension techniques to act upon that information scent. So in this study, I used a think aloud protocol with 13 students who were about to graduate from UC San Diego and with the intention of getting a software engineering job. And with this think aloud study, we screen recorded what they were doing on their IDE, and we also collected their verbalizations as they thought about and reasoned during the activity. So from the text and from the video, we extracted their information sense, we extracted the foraging activities that they used, and we also extracted the diet, the code and the documentation that they were consuming. And with all 3 of these sources of information, we created models of students' program comprehension process. And from this model, we identified students' struggles to actually understand the code base. Now, we uncovered 4 key student struggles. I'm just going to talk about the first one primarily today, which is that students exhibited an over-reliance on opportunistic searches. So opportunistic searches are things like browsing file names or scrolling within a large file to happen upon the relevant piece of code. This is in contrast to what professional developers tend to do, which are called structurally guided searches. They're able to pick up on a class or key attribute and follow how that structure or object is changing or is modified throughout program execution, or even a static analysis to see when a class or method is called. Students also demonstrated poor use of using documentation, especially to get started on the task. Students tended to get stuck at their first relevant code location. So when they found a relevant piece of the code base, even though they did need to modify other files, they tended to localize all of their comprehension and changes in that first relevant code location. And finally, students, when they got stuck on irrelevant lines of reasoning, were unable to abandon them and wasted a lot of time pursuing an irrelevant line of reasoning. So just to give you a sense of what we were able to find here, this is a count of the foraging activities that students used to understand the code base. You can see the opportunistic searches on the far left is the count of the number of times that they were browsing file names or scrolling within a file. Now, to be clear, everybody does this when they're trying to understand a code base. We do look through file names, and we do scroll within a file. But what is surprising is the lack of structurally guided searches that students were engaging with. You can actually see some students never use features like go to definition or find all references, which are helpful to see the relationship between different objects in a code base. And then I also get a question, why is global keyword search not characterized in either of the two? The literature is sort of split on whether global keyword search is an opportunistic technique or a structurally guided technique. Sort of depends on what keyword you're searching for and when you're searching for that. If you're trying to find where a specific variable or class is used versus doing a very general search about maybe an ambiguous word and scrolling through the many results that the global keyword search might show you. We were also able to compare our findings of software engineering students to what the literature has shown are struggles of professional software developers. We're also able to see that exact gap between how our students are comprehending code in a large code base and how developers tend to undergo the same process as well. For example, you could see that our students tended to over-investigate code, getting stuck on those irrelevant lines of reasoning, whereas a common process for a professional developer is to try to avoid investigating code in too much detail, to not spend too much time investigating something that may not be relevant. Now, after identifying, yes, go ahead.
So the left-hand circle in your Venn diagram is based on evidence you collected in an experiment.
Correct.
What is the right-hand circle based on?
Yeah, so this is a collection of works that were in our related work section and what they had found from empirical software engineering research. So these were either lab studies with developers working on maybe a different code base that they hadn't been working with, or they're based on observations of developers in their sort of natural setting working in their team. And so this is, to be clear, not a comprehensive list of the struggles or the effective techniques that professional developers do, more of like a synthesis of how our findings are placed within the broader empirical software engineering research. Awesome, let's keep going. So after identifying these student struggles, I created a course with my advisor at UC San Diego called Working with Large Code Bases, which is meant to be a curricular approach to industry preparation. The idea here is that students get experience working with multiple large code bases throughout the term. In this course, students learn about program comprehension and code navigation techniques. They learn about code quality and testing in a large code base. Then I sought out internal funding at UC San Diego to improve this course after its first iteration, to create an online textbook for it, and to introduce material related to AI-assisted development, which I'll be talking about in the last process. Now, the final phase of this line of work is to evaluate the impact of our course. And this was actually a study that we just did last Monday at UC San Diego. So we got 50 students who had completed our course, 50 students who are about to graduate who have not completed our course. And we asked them to do a task in a new large code base. And we wanted to compare their performance on how correctly they implemented the code modification, wanted to see the code quality of their final commit, and also observe students' program comprehension process to see if they were engaging in some of these structurally guided searches. Now, to actually assess students' program comprehension process, I created a simple VS Code extension to actually track students' IDE interactions to see how they were engaging with some of these code navigation features that I found in my earlier work. It can track things like scrolls, go to definition, global keyword searches, etc. The impact of this line of work is that I uncovered student struggles to comprehend and modify large code bases, which was actually a gap in the computing education and software engineering literature. And as a result, my course that I created with my advisor was originally an elective course and now is going to be a core course at UC San Diego, not just a electives or special topics course. Early surveys from the course showed that students increased their self-efficacy in their belief to complete relevant software engineering tasks. And more importantly, we're offering an equitable way for students to gain valuable experience working with large code bases. And the materials for this course, now that I have added material related to AI-assisted software development, are featured on the GenAI and CS Education Consortium page for instructors to actually take materials directly from the lectures and assignments that we offered. I've also done work to understand students' code quality defects in large code bases, and then more recently was selected for an international working group to create assignments and lecture examples and activities for CS1 instructors to introduce code quality at that level. This is important because code quality is typically not taught in introductory computer science classes, but as I'll talk about in a little bit, I think code quality is becoming more important in the age of GenAI. Awesome. With that, let's talk about student AI collaboration for programming. Now, it's no secret that GenAI is pervasive in the software engineering industry. The Dora report from Google last year showed that adoption is ranging from startup companies to established tech firms and is impacting the entire software development lifecycle from requirement solicitation to deployment. Now, a recent study from Pharos, and by recent, I actually mean data up until 2025 and the middle of 2025, and that'll be important in a second, used telemetry data to study 10,000 developers to see the impact of AI-assisted software engineering. What they found was that task completion rate increased by 21%, so developers were able to fix and complete issues faster. However, the amount of time spent on code review increased by 91%, and the study pointed to this as a bottleneck. The amount of code in each pull request had actually increased by 154%, and the number of bugs introduced by developers also increased by 9%. Now, let's take these numbers with a grain of salt. I do think we see improvements every couple months, and actually from the end of 2025 and beginning of 2026, there was a big leap in the capabilities of these LLM models, especially for software engineering tasks, specifically with, I think, Opus 4.6 and then GPT 5.3, who had like significant improvements in completing software engineering tasks. Oh, and also, yeah, just in the last 2 days, I saw posts about JetBrains creating an agentic development environment that I think was just released yesterday. And then Anthropic actually launched a code review tool specifically given these issues about the increased need for code review in the software engineering process. So now, how is computing education reacting to this? Well, in computing education, we do recognize that there's this end goal for students to graduate as productive and responsible users of GenAI. But to reach that end goal, we need to develop best practices for teaching computer science in the GenAI era. But to develop those best practices, we need to understand how students are using these AI tools, how they're using them well, how they're using them poorly. And the earliest work in this space was to understand the capabilities of these LLMs. Every 2 to 3 months, these studies became outdated because these models kept getting better and better. And so now, my work focuses on understanding how students collaborate with these AI tools. And then my current and future work is to develop these best practices for teaching computer science in the age of GenAI. So when I say something like student AI collaboration, what exactly do I mean by that? I think of it in 2 elements. The first are students' interactions with the AI tool. How are they prompting the tool? How are they engaging with the output? And the second are students' attitudes towards GenAI. And I'll talk about what I mean by attitudes, which are very broad, in a second as well. So the line of work that I want to talk to you all about today is about trust in GenAI assistance. Okay? Trust regulates how we use AI tools. I think of this like the scales of justice in the legal field, where if a user's trust in GenAI is too low, then they won't use GenAI when they should and miss out on some of the benefits of it, like improved productivity and reduced frustration, improved well-being. But if our trust is too high, evidence shows that we're more likely to engage in over-reliance behaviors and introduce insecure or even incorrect code that these AI models have introduced for us. Instead, calibrated trust is the ideal outcome, where students and developers are using these tools productively and responsibly. The issue with studying an attitude like trust is that many studies conduct a static analysis of trust. They'll use surveys or interviews to capture trust at just one point in time. But trust is actually a dynamic attitude that is formed and changes over time. So these single measurements don't tell us how that trust was formed and how it may change with increased experience and exposure to an AI tool. So to address this gap, my first study was to understand how and why students' trust changes when they're working with GitHub Copilot in the context of a large code base. So using my course, Working with Large Code Bases as context, I studied how students' trust changes when they were first introduced to GitHub Copilot in a large code base, and how it changed with increased exposure to using the tool for more complex tasks in a large code base. Now, in the short term, students' trust increased. They were surprised by the capabilities of these tools. But as they used GitHub Copilot to complete assignments that we had in the course, students' long-term trust decreased. So we wanted to understand why we saw this change in trust. We used thematic analysis, gathering students' open-ended perceptions of using these tools. And we found that students valued learning the basics of natural language processing. We taught them a bit about probability distributions, context, and non-determinism, so they had an understanding of some of the inner workings of these models that they're using. Students also are making frequent perceptions of the correctness of the output. Obviously, when they see some explanation or code generated by these tools, they want to know, is that correct output? And lastly, students valued being aware of key features in the tools that helped with working with large code bases. For example, using the context of the code base as context when they're making a specific prompt to the AI assistant. And just to give you an idea of how I think about these AI assistants, an IDE is perhaps the most common tool that developers and programmers use. These AI assistants are similar tools. And just like my earlier work showed that students and even some developers were unaware of some of the features in these IDEs, I think we have a very similar process happening with many of these AI assistants and agents, where there are a variety of features that can be leveraged for effective collaboration, but students and developers may just be unaware of those features. Now, building upon this, I wanted to study how students are actually interacting with GitHub Copilot. So I studied students' prompts that they were giving to GitHub Copilot as they were doing a task in the large code base. And what we found was that 2/3 of students in our large code bases course asked Copilot to implement the entire task for them in just a single prompt. That itself is not a bad trait. I think students should try doing that, and if it works and gives correct output, that's totally fine. But as of 2025, this model typically gave an incorrect or incomplete solution. And as a result, students engaged in a manual debugging and manual testing process to fix or verify the code outputted by the GitHub Copilot, showing the importance of some of these traditional software engineering skills to effectively collaborate with AI assistants. And then more recently, we have this phenomenon of vibe coding. Vibe coding is a very interesting paradigm change in programming, where the user, the developer or the student, is giving a lot of trust to whatever agent is doing the programming. But the programmer also has less control over the situation and less control over the outcome. This is really important, this idea of control. There's a theory in computing and education called control value theory, which says that students react positively emotionally when they're in high control of a situation and they feel that the task that they're doing has high value or is meaningful to them. And emotions are important because it impacts students' retention and persistence and sense of belonging in the field. But vibe coding does change this approach to programming. So we wanted to study how do students in introductory courses and upper division software engineering courses engage in the process of vibe coding. And what we found was actually that upper division students were more capable in expressing the specifications to the AI agent, and the lower division students in CS1 did not create as high quality projects at the end of the 75-minute session that we had in the Think Aloud study. But what we also found is that, especially at the lower division level, CS1 students were engaging in notions of version control despite not being introduced to version control at this point in the curriculum. For example, in the agent that we use, it was on Replit, it has this checkpoint feature where you can sort of keep a state of your project when you're happy with its current state. And students were actually using this checkpoint feature when they were happy with the current state and were worried that the next prompt might lead to a completely different implementation or some bug that they were unhappy with. Students also had to heavily rely on requirement specification, where they were engaging in end-to-end testing to see whether the prototype that the AI agent produced was correct, and then had to initially specify the requirements and then re-specify and add some specific constraints based on whether the testing that they were doing was working or not working. Now, the impact of this line of work is that I understood student AI collaboration, a small part of student AI collaboration. There's certainly more work to be done beyond the CS1 level. Like I mentioned, a lot of computing education research tends to focus at the CS1 level, but we were looking at the context of software engineering tasks. And the impact of this is that the course materials that I created are in the GenAI and CS Education Consortium. And I was just recently selected to participate in another international working group about developing learning objectives and course materials to improve students' AI literacy in computer science courses throughout the curriculum. I've also been involved in the earliest work on students' vibe coding practices. And like I mentioned, some software engineering processes are appearing earlier in the curriculum, leading to considerations of how we should revamp the CS curriculum in the age of GenAI. And we also saw that upper division students collaborated more effectively, sort of dispelling this notion that anybody could vibe code, even with not so much technical background. So there's further work to be done here to understand what those skills are to lead to effective vibe coding practices. All right, now I want to share my vision for my future work. So programming is completely shifting in the skills that are used in the process. So it's easier than ever to create code, but the process to create that code has changed. There's less of an emphasis on a skill like code writing from scratch, and perhaps greater emphasis on skills like program comprehension, code review, and debugging. Now, there's two disciplines, research disciplines, that are significantly impacted by this change in the programming process. It's empirical software engineering research, computing education research. Let's walk through some of the differences between the two. Empirical software engineering research tends to study professional developers who, for the most part, were trained without GenAI in the classroom. And the goal of empirical software engineering research tends to be developer productivity. Now, as a result, we have these amazing artifacts, things like the Dora report, Stack Overflow's developer survey, and a whole range of software engineering tools to improve the day-to-day workflow of software engineers. Now, in computing education, we actually use many of the same methods, but we have a completely different population and different goals. We don't study professional developers, but we study novice programmers who are still learning the fundamentals of programming and computer science. Our goal is not productivity, but it's promoting student learning. However, our students are increasingly using tools like ChatGPT and GitHub Copilot, which comes for free in VS Code. And now these tools are not necessarily designed to support student learning. And so my field has this question over our heads, which is, what happens when today's students become tomorrow's developers? Now, I have 4 questions that I want to address in my future work. The first is that in the age of GenAI, what processes should we be teaching to students in the curriculum? How should we be teaching these processes? Who should we be teaching these processes to? And when should we introduce these processes? Now, the first 2 I view as a more 5 to 10-year research horizon, the later 2 part of a broader research program. So I'll just focus on the first 2 today. What processes should we teach? I'm well positioned to study both ends of the undergraduate CS curriculum, from CS1 to upper division software engineering. And just as I've done to understand student struggles with working on large code bases, I want to understand student struggles in the AI-assisted programming process. For example, now, students are having to interact with the output. So how well are students able to understand, verify, and improve on the output from these AI assistants and agents? And how well are students able to elicit requirements and communicate those requirements, elicit requirements from a real-world problem, and then communicate those requirements to an AI tool? And the impact of this line of work would be helping reshape the CS curriculum from the CS1 level to upper division software engineering level by creating specific learning goals that instructors should be targeting in their courses. But how do we teach these processes once we identify which skills are important? Well, I've talked to you today about 3 programming processes, and a common thread throughout all of them is that I identified observable, IDE level interactions that students had when engaging in each of these processes. For incremental development, I considered how much code was added or changed in between compilations. For program comprehension, I looked at how students interacted with the IDE to navigate a code base. For student AI collaboration, I looked at how students were prompting these tools and reviewing the output. Now, in the future, I envision an IDE-based programming process coach that's able to take students' input of IDE interactions and lead to some of those pedagogical innovations I mentioned earlier, like process-level feedback, personalized coaching, and new grading schemes. Like Ben mentioned earlier that I am learning tennis right now, and the best way for me to actually learn tennis would be for my coach to be standing right behind me, and after every point, give me feedback on my footwork and my weight distribution. Unfortunately, we can't do that in computer science. We can't teach programming like that where we have somebody coaching students at every moment that they're working on programming. But a proactive tool like this would be able to actually scaffold and coach students throughout the programming process. And the impact of this would be individualized coaching at scale, where we'd be able to give students this important process-level feedback. Now, lastly, as I've gone around the country and talked to different instructors about how they're feeling in the age of generative AI, a very common question I hear is, what do formal learning environments, or more specifically, what do my computer science courses look like in the age of GenAI? So for example, what do lectures look like? How much space is there for live instructor demonstrations versus students collaborating and working together when they're actually all in the same physical space together? So I want to understand what are the best lecture techniques to teach students the processes that we identify. What should assignments look like? Typically, assignments are a way for us to assess student learning. These are formative assessments. And they're also somewhat indicative of student learning. But what do assignments look like when GenAI is able to correctly implement many of these programming tasks? And lastly, what should assessments look like? How frequently should I be having assessment? How do I know that my assessments are actually designed to address the skills that I want to be assessing on the exam? Now, given my experience conducting term-long classroom experiments, I want to explore the possibilities in each of these aspects of formal learning environments to understand the best ways to design computer science courses in the age of generative AI. And the impact here would be changing the way that we teach computer science in each of these aspects. On a concluding thought, I want us to all imagine a typical programming course of tomorrow. We'll still have anywhere from several dozen to several hundred students. But when they work on the programming process, they may be working with an AI assistant, but they may also be having a tool to coach them along the way. And when the deadline for that assignment arrives, the students will still submit a version of their code, but they may be working on more meaningful projects like my collaborators Leo Porter and Dan Zigaro have written about, where students might be creating games or editing images or doing larger scale data analysis than they were able to before. And when we have to grade these students' submissions, we may still look at the correctness of their solution, but we may also consider other outcomes like the creativity of the problem that they chose to solve, the quality of the code that they submitted, and even how well they comprehend or understand the code that they've submitted. Thank you all for listening to my talk.
That was a fun talk. Thank you. So when you talk about large code bases, I was wondering if you could talk about kind of what you mean by large and how different scales of code bases impact students and what they excel at, how you teach that.
Yeah, that's a great question. So in the research methodology, we did quite a bit of piloting with different code bases to see which ones were good for like a lab study or a classroom study. And some of the literature in empirical software engineering research, for example, Amy's work from about 20 years ago that looked at how developers also forage for information in a large code base, they used the JEdit code base, which was about 60,000 lines of code. Some of the other studies we looked at in empirical software engineering were about that size, which to be clear is small. That is not a large code base by industry standards. So when we were having to decide what code base to choose, we wanted it to be large enough such that students could not read all the files of code and understand it, but we wanted it to be small enough such that it could work in maybe a 90-minute task think aloud study, or easy for students to run on their own machines rather than have to use a server or something when they're in our course. Did I fully answer your question, or was there another part? How big was the code base that we used? So we have students work on a few different code bases. And the Working with Large Code Bases course, they're working on the idle-lib code base, part of the CPython open source project. That's about 25,000 lines of code. They also work on a different code base called Thonny, which is also a simple IDE. I think that one maybe also around 30,000, or maybe closer to 60,000. I don't remember the exact numbers, but in the process, we wanted it to be sufficiently large such that in the time that they were given, they can't understand all the files and lines. Yeah.
I was just curious, I mean, do you think, how long do you think students are going to be coding? And so how important is it to teach them coding? And if so, what percentage of our curriculum should be focused on code?
Yeah, you've laid out an amazing research question that I would love to answer over the next few years. But I'll also say that given the change in the coding or programming process, it actually gives us an opportunity to move the way that we teach computing a bit beyond just a focus on programming. So for example, a big part of software engineering is actually not programming. It's understanding a real-world problem, understanding the specifications that you need to build software for, and then you create that with, whether you're using AI tools or not. You need to verify the correctness of your approach. You need to make sure that it can scale and support, many users, for example. Then you need to maintain that. So I think what we have now is actually an opportunity to engage these other aspects of programming that are not the coding part itself, but the real-world human aspects of programming that we're now open to be able to solve. And just to give you a more concrete example, one concern with computing education is that we suffer from a lack of diversity in the field. And one of the reasons that's been posited for that is that in the first 3 computer science courses, students are not exposed to some of the powerful applications of computer science. They're solving very trivial assignments or maybe working with assembly code and C code that is still valuable for their learning, but they don't get to see some of the powerful applications until much later in the curriculum. And by that time, we may have lost many of the students that otherwise would have stayed in the field. And so we now have an opportunity to bring some of those benefits earlier in the curriculum where we can engage those societal impacts of computing in even computer science 1 courses.
All right, thanks, Ben. So in addition to all the wonderful things that you covered in this talk, I think something we often try to promote in our classes is peer learning and collaboration among students, not just with AIs or a relationship to the instructor.
Yeah.
However, over the past year, for better or worse, I've noticed, for example, the number of final projects in my project-based courses has more than doubled. And correspondingly, the team sizes have cut in half, and the number of individual projects are much higher. And this seems to conform with other reports and articles suggesting an atomizing effect that generative AI use can have on existing social fabrics of collaboration and so on. So I'm curious if you saw similar things as well in your own classes and how you think about that in terms of larger problems in curricular design.
Great question. So yeah, the research is showing that students are going to office hours less and sort of siloing themselves into their own help-seeking outlets. So it makes me question, like, what is the value of spending $30,000 a year to come to a college, and what is the value of the degree that they're getting at the end? And I think the unique benefit that we have in a college environment is that everybody is in the same geographic location. We have this community of practice of learners that are together. And what we've done, for example, in my classes is actually removed many of the office hours, okay? Every hour of a TA or tutor's time is so valuable. And in an empty office hour room that nobody is visiting, I think that hour is wasted. So we've significantly shrunk the amount of office hour times, replaced it with times where students do have to come in with a group and communicate with a TA or tutor in a study group. So they can either work together or just work in the presence of a TA for 1 hour, kind of like a lab section. And what we've also done is introduce oral exams, where students have to correctly implement their programming solution, maybe with AI, maybe without, and then explain the choices that they made, explain that they understand some of the design decisions, we'll pick out specific lines of code and ask them to explain it. And that aspect of technical communication in the last 15 years has consistently been a part of the academia industry gap that industry managers tell us our students are suffering from, but we have not done anything to really address that. Recent work from, I think, like 2 weeks ago, there's an ACM task force to understand how educators are reacting to GenAI. One of the most common things, the most common thing, is increasing the value of assessments, reducing the value of assignments. I think that's what a lot of instructors have done. The second most common thing was using oral exams. And so people ask me, how do you scale oral exams? Well, you have to cut back on some other resources. That other resource is something like office hours. Yeah.
Yeah, thank you.
Yeah. Yeah, right behind you, I think.
Thank you. So in your results that upper division software engineering students generally did better at vibe coding than CS1 students, which makes intuitive sense, I think, for a lot of reasons. I'm curious, were those upper division students primarily students who had taken introductory computer science and been introduced to programming before GenAI became as powerful and ubiquitous as it has become? Or had many of them perhaps taken CS1 or early courses during the age of GenAI? And in either case, how do you think about maybe reassessing and understanding those results moving forward as more and more students will have spent their entire programming careers with GenAI as an available and powerful resource?
Yeah, that's an amazing question. So for the first part of like what did the students in our data set look like, they would have taken introductory programming in 2022 or 2023. At UC San Diego, we have a few different instructors that teach CS1. One uses GitHub Copilot almost at like week 3 or week 4 of the curriculum. Some maybe don't introduce GitHub Copilot at all. So we would have to really revisit the data, see which version that they took. But what your question is getting at is actually that concept of cognitive debt that I mentioned earlier, where relying on using an AI tool can slowly lead to this accumulation of cognitive debt, where students may not even understand some of the more basic like syntactic elements of the language, or not understand some of the principles of how iteration actually works. And so I don't have a clear answer to your question of like what would be the effect, but I think that's something that warrants a lot of attention to in a research sense, where if we teach students in an introductory computer science class some more AI-forward programming, what is the actual aspects of cognitive debt that are piling up, and what are they missing by the end of the curriculum that we need to be reshaping our curriculum to actually address? Hope that helps. Yeah. Yeah.
All right, well, we are at time, so thank you very much, Anshul, and thank you, everybody, for your
Thank you.
questions.